Okay, this example we're going to be looking at some basic vocabulary for polynomials. So we have the polynomial here, x cubed plus 5x squared minus x to the fifth plus 4. We're supposed to first write it in standard form. The standard form for a polynomial means that the highest exponent will come first, and then the exponents will be decreasing from left to right. So as far as exponents go, the first one has an exponent of 3, second term has an exponent of 2, we have 5, and then we have 0 because we don't have an x with that one. So 5 is the highest exponent, so we'll move that first. So negative x to the fifth. Then next would be x to the third, so plus x to the third, making sure we keep the signs correct as we rearrange. Plus 5x squared, and then plus 4. Now the next thing we're asked is degree. Degree is the highest exponent of a polynomial in one variable. In this case, our highest exponent was 5, so the degree is 5. And lastly, leading coefficient. Now, leading coefficient deceives people because of the word leading. Leading coefficient is always the same regardless of whether it's in standard form or a mixed up order. Leading coefficient is the coefficient with the highest powered term specifically. So regardless of if I'm looking at the original or the version in standard form, the leading coefficient is still coming from the same term, still coming from the x to the power of 5 term. And the leading coefficient here is -1. There is no coefficient beside x to the fifth, so it's implied to be a 1. Because of the negative sign, it's negative. Okay, in this example, we are going to be describing the end behavior of the function graph below. Now, end behavior, all that really matters is the ends of the graph. There's two sides to this. There's the left side and the right side. Two end behaviors going on. I usually start off by using words, and then I go into the algebraic notation here. So left side and right side. So left side, if I start in the middle and move towards the left, what's happening to my graph? Well, you can see the graph is going down. So we say down. On the left side, the graph goes down. And if I look on the right side, starting in the middle and going to the right, you can see we are also going down. So both sides happen to be going down. Now, this isn't really that great of a description. We usually use more mathematical terms, so let's turn it into mathematical to describe it. Left is an x descriptor, so I'm going to say x approaches, which is what the arrow is representing, the word approaches. So x approaches, and then on the left side are negative x values, so negative infinity. And then for down, down is a y descriptor. So y approaches, well, what type of y values are down? Negative y values are down, so negative infinity. And then I'm going to do the same thing for the right end behavior. Right is an x descriptor. What type of x values are on the right? Well, positive x values are on the right, so x approaches positive infinity. And down, well, down is a y descriptor. Y approaches negative infinity because negative y values are down. When you're doing end behavior functions, a lot of times they will have both left end behavior and right end behavior. You'll notice that the x approaches will never be the same because it can only do one thing on each side of the graph. However, the y direction can be repeated or it can be different just depending on the particular graph. Okay, in this example, I'm going to do end behavior of the function graph below. So again, we have two sides to the end behavior, a left side and a right side. Now, starting with the left side, I'm going to start in the middle of my graph and then follow it in the left direction. So just kind of following it. You'll notice at first I start to go down, but end behavior is about what happens in the long run. In the long run, we are going up. So the left side of this graph is going up. Now the right side, if I start in the middle and go to the right, At first, you see that we are starting to go up. However, again, what matters is in the long run, if we continue, you see the function goes down. So on the right side, we are going down. Now we just have to turn this into mathematical notation. So left is an x descriptor, and negative x values are on the left. So x approaches negative infinity. Up is a y descriptor. So y approaches, well, what type of y values are up? Positive y values. So the left end behavior is described as x approaches negative infinity, y approaches positive infinity. And then for the right end behavior, as x approaches, right is an x descriptor. Positive x values are on the right, so positive infinity. We are going down, so y approaches, well, what type of y values are down? Negative, so negative infinity. And there we go, there's the end behavior for this function. Okay, in this example, we have a simple polynomial kind of graphed here with a bunch of variables that we can use the sliders in Desmos to check out the end behavior of a polynomial. Now, currently with the way it's set up, this variable here is set up to be the degree. And I can make this a more complicated than what it actually is by adding more variables. But this should be enough to kind of show the situation. I'm going to move some of these variables here around. The degree I'm going to leave alone for now, but just focus on the end behaviors. Currently, the end behavior is up over here, and then down over here. My toolbar is kind of in the way, so I can't do a good job on writing there. But it's down on the left side, up on the right. So let's go ahead and move some of the sliders here and see what happens. I'm going to start with F. Looking at F, does that change the end behavior? If I can click in, come on. There we go. Okay, so moving in F, if we look at the end behavior is not changing at all. This graph is just going up and down. So F does not affect end behavior. Okay, so I'm going to leave it kind of there at -1. Next, I'm going to look at A. A is the leading coefficient here, so if I move it to the right, it's not really doing anything, but then left it is doing something. You can see that the end behavior has flipped. So it looks like A is affecting the end behavior, so I'm going to put a star right there, which is the leading coefficient. I'm going to abbreviate as LC. Now I'm going to move on to C and D and check those out as well. Let's see, get back into the graph. Okay, C, if I move C around, you can see it kind of bending up and down. It's not affecting the end behavior though, because the left side is still pointing down and the right side is still pointing up. So C does not appear to affect the end behavior for this cubic polynomial. Currently a cubic because the degree is 3. And then same thing goes for D. Nothing's really happening there. So the only one here so far that we looked at appears to be the leading coefficient. I'm going to go ahead and hit play real quick with these spinners. And no matter what combination we look at, if we are not affecting, if we are not changing the leading coefficient, you can see the left side is still always down and the right side is still always up. So let's go ahead and pause those. Put them back to something where we can actually see. Okay, there is another thing that also has an effect on the end behavior of the polynomial, and that is the degree. So I'm now going to move that degree slider. If I move it, you can see that while when it's a third degree, left side is pointing down, right side is pointing up. But now as a fourth degree, both sides are pointing in the same direction. And then back to 5, left side is down, right side is up again. So you can see it alternates as I increase the degree between both going up and one going up and one going down, based on whether it's even or odd. So there's two things that affect the end behavior of the polynomial. The leading coefficient, it basically affects whether it's the normal orientation when it's positive or the reflected orientation when it's negative. and the degree of the polynomial. If it's even, both sides point in the same direction, whether they're both up or both down in the case of having a negative leading coefficient. And then if it's odd, they do opposite directions, whether it's left side down, right side up, or left side up, right side down, depending on the combination. Those are the only two things that affect the end behavior of a polynomial. So this chart here kind of summarizes the end behavior of a polynomial. You can kind of see that for the end behavior, we have if the degree is odd, it will fall in this column, while if it's even, it will fall in this column. Then we can also look at the leading coefficient, positive falling in the first row, negative falling in the second row. We can figure out the ends of the graphs with these little arrows and use that to help us with end behavior. But the gist is, for even, both sides point in the same direction. If it's a positive leading coefficient, because there's no reflection, they're both up. With negative leading coefficient, kind of creates a reflection, meaning both down. Odd, the traditional way is left side down, right side up. However, if the leading coefficient is negative, we get that reflection, having the left side up and right side down. Okay, in this example, we're going to describe the end behavior of a polynomial. F of x equals 5x to the third plus 6x minus 9. Now, end behavior of polynomial is determined by two things, the degree and the leading coefficient. The degree of this polynomial is 3, because that's the highest exponent, while the leading coefficient is 5, because that's a coefficient with the highest powered term. The degree here is an odd degree, so no, both sides are doing two different things, while the leading coefficient is positive. So I know that the basic shape of the graph will look like this, with the right side up and the left side down. If we do end behavior from this, I said the left side was down, left arrow points down, right arrow is up. Just got to turn that into mathematical notation. The left arrow, or the left side, would be x values, and x approaches, well, negative x values are on the left, while down is a y descriptor, and negative y values are down. For the right end behavior, we have the right side, which is x descriptor. X approaches positive infinity, while we go up, which is a y descriptor. Y approaches positive infinity as well, because positive y values are up. Okay, in this example, we're going to describe the end behavior of the polynomial f of x equals 4x squared minus 9x to the fourth plus x to the third. The only thing that determines end behavior of a polynomial is its degree and leading coefficient. But it's very important to pay attention. This one is not in standard form. The highest exponent, or the degree, does not come first. The term we want to focus on is this second term. You could either just focus on this or rewrite it in standard form first before trying to figure things out. Writing in standard form, it would be negative 9x to the fourth plus x to the third and plus 4x squared. But regardless of which form you're looking at, the degree is still 4, because that's the highest exponent. And again, regardless of which equation you look at, the leading coefficient is still going to be the same thing, because the leading coefficient is with the highest powered term, which is negative 9. It's not about being first. Leading coefficient is referred to as a leading coefficient because it's the first term if it's in standard form. But that's only if it's in standard form. So again, leading coefficient is just the coefficient with the highest powered term. Now that we know this, we can look at the, or figure out which basic graph it follows. So degree is even, and the leading coefficient is negative. Because the degree is even, I know both sides are doing the same thing. but because the leading coefficient is negative, I know that both sides are going to be pointing down. So it's going to match this graph here. With that, I know the left side is pointing down, and the right side is also pointing down. Which you don't need to draw this graph, you can just go straight to it as long as you can picture the graph in your head. The left side is x values, x approaches, well, negative x values are on the left, so negative infinity. Down is a y descriptor, so y approaches negative infinity because negative y values are down. Right is an x descriptor, x approaches, well, positive x values are on the right. And down is a y descriptor, so y approaches negative infinity for negative y values being down. Okay, and just quickly elaborating on the difference between relative extreme and absolute extreme. If I look at this graph here, just a simple graph without even a grid, these are all extremas. They're different type of extremas, but they're all extremas. This one right here is a relative max. Relative are also called local extrema. This is a high point, but it's not the highest point on the graph. This one right here is a relative min. It's a low point, but not the lowest point. Again, it could also be called a local min. The other type of extrema is the absolute extrema. This one doesn't have an absolute minimum, but it does have an absolute maximum, which is absolutely the highest point on the graph. These are also called global. So, and they could also just be referred to as max or min without the extra word. So you can also picture this like in a global perspective on planet-wise. An absolute extrema as a visual representation would be Mount Everest, because it's the highest point on the planet. And a relative extrema would be like a hill in your local town, which would be a high point, higher than stuff around it, but it's not the highest point. And when we're discussing polynomials, oftentimes you'll hear extrema referred to as turning points because the graph changes its direction, so often referred to as turning point. Okay, in this example, we're going to be describing some key characteristics for the polynomial function, and we're going to have to approximate in some cases as we need to. Now, some of these values are, actually all of these values are pretty much a review from earlier lessons. So if we look at the first part here, A is asking whether the polynomial function is odd or even. So as far as whether it's odd or even, because both sides do different things, left side is going down, right side is going up, I know that this is odd. It's an odd polynomial function. Or odd degree is probably a better description. The next is B, to describe extremas. So it looks like extrema-wise, looks like we have two extrema, one right here and one right here, none of which are perfectly on. The one on the left here is approximately the order pair negative 2.5, and it's just under positive 1. It might be hard to see on the graph, but it's just under positive 1, so I might put 0.9 or something. And this is a high point, but it's not the highest point on the graph, so it's a relative max. The other point is it's just off the y-axis. It's really hard to tell on this particular graph because it's a little blurry, but it is just off to the left of the y-axis. So I might say negative 0.1, comma, I think it's just below negative 6 as well. So I'm going to say negative 6.1. We do have to approximate some of these values as we go. And this is also a relative one because it's a low point, but not the lowest point. So it's a relative min. The next thing we need to do is where the function is increasing, decreasing. So for increasing, decreasing, remember we split it at the extremas. That was not a very straight line. And then right there, this separates my graph into 3 parts. Negative infinity until that first extrema, which had an x value by our approximation of negative 2.5. Then negative 2.5 to negative 0.1. And then from negative 0.1 to infinity would be the 3 intervals. Since we're doing increasing, decreasing here, as we move from left to right, this first interval we're going up, while the second interval we're going down, and the third interval we're going back up again. So we are increasing on the intervals negative infinity to negative 2.5 and negative 1 to infinity. And we're decreasing. I totally spelled that wrong, but I'm going to just keep going. From negative 2.5, comma, negative 0.1, and that's a negative 0.1 up here. I just missed my decimal place. There we go. Next up is D here, intercepts. So we have 3 intercepts, it looks like, at negative 3, negative 2, and 1 for the x-intercepts is negative 3, negative 2, and 1. And for the y-intercepts, I think it is exactly at 6. A little hard to tell because all my lines and dots there. I believe it's exactly at negative 6. There we go. And then we just have one more part, E, to do intervals of positive and negative, and that's about above or below. So for positive, negative, remember for positive, negative, we split the graph here at the intercepts, the x-intercepts. There and there. This splits the graph into 4 areas, and it's getting a little messy on my graph, so I'm not going to write all the intervals like right below like I prefer to do. Here is the first interval, and this interval here. These 2 intervals are below the x-axis, this portion here and this portion here. So because they're below the x-axis there, those are the negative intervals. The first one starts at negative infinity and goes until that first x-intercept, which is at negative 3. The second one picks up at negative 2, the x-intercept negative 2, and goes until the last x-intercept of 1. The other 2 intervals are above the x-axis, so those are where they start and end. So those are positive. They start from negative 3 to negative 2, and from 1 to infinity. There we go. Okay, in this example, we're supposed to find the average rate of change for the function f of x equals negative 0.5 x to the 4th plus 3x squared plus 2 on the interval 0 to 2. So first to start this, remember that average rate of change is just another way of saying slope. So, since we're looking for slope, we can use any of the slope formulas. I'm going to start off with the function notation formula. So f of b minus f of a over b minus a. So remember that in this interval, since it's an interval, both of those numbers are the x values. So in the function notation formula, the 0 is a and the 2 is b. Or if you're talking about the algebra 1 notation with the x1s and y1s, the first value is x1 and the second one would be x2. If we're talking the algebra 1 y2 minus y1 over x2 minus x1. With that piece of information, I can replace a and b. So f of b, which is 2, minus f of a, which is 0, over 2 minus 0. Now the problem here is we don't actually know what f of 2 and f of 0 are, so we are going to have to go and find them. F of 0 just means to plug in 0 into the equation, so let's start with f of 0. So we would have negative 0.5 x to the fourth, which is now 0 to the fourth, plus 3 times 0 squared plus 2. Since we replaced all the x's with 0, the first two terms are all going to be canceled out, turned into zeros, and then add to 2, we get overall 2, meaning that the y value for f of 0 is 2. Now we're going to do the same thing with our second x value, which is 2. So f of 2, second x value, that b. Replace x with 2, so we'll have negative 0.5 times 2 to the fourth plus 3 times 2 squared plus 2. 2 to the fourth is 16, so we have negative 0.5 times 16, which is negative 8. In the middle term, we have 2 squared, which is 4, and 4 times 3, which is 12. And then plus 2 on the end gives us a total of 6. So we now know that f of 2 is 6. So we can replace f of 2 in our slope formula with 6 minus f of 0 we found to be 2. So I'll replace it with 2. And then this is over 2 minus 0. Now we just have to go through and simplify. 6 minus 2 is 4, and 2 minus 0 is 2. So 4 divided by 2 is 2. You'll get the same answer if you use the y2 minus y1 over x2 minus x1 formula. The first x value is 0, and the first y value is 2. Then the second x value is 2, and the second y value is 6. And there we go. You would still get the same answer plugging it in. Okay, so in this example, we are going to be sketching a function while knowing its characteristics. So I'm going to kind of get myself a grid set up first before I do anything. So our first description is about positive and negative. Okay, so positive and negative, the intervals are negative infinity to negative 4 and negative 1 to 4 for positive. And then for negative, it's negative 4 to negative 1 and 4 to infinity. Now, important to know is that positive and negative are connected, and you go from positive to negative or negative to positive at the x-intercepts. Okay, so I know that there are x-intercepts at negative 4, negative 1, and 4. So I can mark that on my graph, 1, 2, 3, 4, 1, 2, 3, 4. I know there are x-intercepts at negative 4, negative 1, and positive 4. Now I also know that the graph is positive on the interval from negative infinity to negative 4, so that would be on this side of the x value negative 4. It is negative between negative 4 and negative 1, so it will be down here between these 2 points. It's positive again, and then it is negative from 4 onwards. It doesn't have to alternate, but a lot of times they do. So that's the positive and negative information. So let's go ahead and check out the second bit of information, which is about increasing, decreasing. So we are increasing from negative infinity to negative 6 or 2.67. and we are also increasing from 2 to infinity, but we are decreasing from negative 2.67 to 2. Now, extrema is what separates the intervals for increasing, decreasing. You stop increasing when you have an extrema and start decreasing afterwards. So we know we have an extrema in 2 spots. We have an extrema, oops, I chose the wrong writing tool, extrema at x equals negative 2.67 and at 2. So those are our 2 extrema, 2 x values for the extrema. Now I know that we are originally decreasing until we get to negative 2.67, and I know it has to be negative in that spot, so it will be about, maybe say here, I don't know the exact y value, but this is just a sketch. And then we know it is increasing after this point, so I know it decreases until we get somewhere down here at negative 2.67. Then we are increasing until we get to the positive 2. So somewhere up here we will be, I don't know exactly where, but that is fine. This just has to be the highest point. And then we are decreasing from then onwards. So now we just kind of have to draw this in best we can, make it a little pretty. Remember that polynomial have smooth curves, no points. So I might have something, if I can not click my toolbar, might have something that looks something like this as my graph. And there we go. Okay, in this example, we're going to determine what the function f of x equal to x to the third minus 2x squared minus 5x plus 6 is behaving on each of the following intervals, or each of the groups of intervals. We're going to use the words increasing, decreasing, positive, or negative for each line, and only use each of the words once. Now we're going to not do this with the graphing calculator. This is just to see our actual skills with interpreting the graph, or interpreting the characteristics of the function from the equation, and just typing it into the graphing calculator would kind of defeat that purpose. So I'm going to start by just kind of observing some of the intervals. You'll notice that some of the intervals have similar numbers to other intervals. For example, negative 2, 1, and 3, which are in the first group of intervals, occur in the last group of intervals. So I know that these two are connected. If the first one describes increasing, then the last one must be decreasing. Or if the first one is positive, the last one must be negative. They are related. The middle two are also related. They share the same numbers. Now with that, we can continue. The next thing I'll focus on is end behavior. So looking at my leading term is the x to the third. The degree is 3, which is odd. And the leading coefficient is 1 because there's nothing there, which is positive. With this information, I know that the graph is going up on the right and down on the left. Now with this information combined with the intervals they give us, it's enough for us to actually answer this question. I'm going to focus on each of these arrows. This first arrow here, as an interval, it would start at negative infinity, and it would go until, well, I don't know exactly what number it goes to. While this other arrow will start at, I don't exactly know where it's starting at, but it will keep going until we get to positive infinity. If we look at these characteristics here, we're going to have to make a choice to focus on either increasing, decreasing, or positive, negative first. It doesn't matter which one we focus on. I'm going to focus on increasing, decreasing first. So if I look at these two arrows and I describe them from left to right, then this first arrow is going up from left to right, so I would say it's increasing. Now, I do want to emphasize it's going up from left to right, not the direction the arrow is pointing, because the direction was for end behavior. But as we go from left to right, it's going up, so it's increasing. And the second arrow is also increasing if we go from left to right. Now, what that tells us is that the interval with negative infinity and the interval with positive infinity are both increasing. So if you look at each of these lines, for negative infinity and positive infinity to be on the same line, that's the one that is increasing. The first line only has one infinity. Second line has none. The third line has both negative infinity and positive infinity on the same line, which means that those are the increasing intervals. And if the third line is the increasing, then the second set of intervals is the decreasing, because they share the same numbers and are related. Now we just have to look at positive and negative, and based on the end behavior here, this right arrow is above the x-axis, or will be above at some point, so it's positive, and the left arrow is below the x-axis, so this interval is negative, which means the interval with the negative infinity is negative, the interval with the positive infinity is positive. Now, that doesn't always hold true where it's the positive infinity is the positive interval. It just happens to be that way in this example. So looking at the remaining lines that we have, here is where I see the positive infinity, which means based on our characteristics that we see, this is the positive intervals, and the last one must be our negative intervals. And there we go. Okay, in this example, we have a hot cup of tea is left in a room that is approximately 40 degrees Fahrenheit. The temperature of the cup of tea is modeled by the equation f of x equals, I'm not going to try to read that, which is the equation in Fahrenheit, where x is the time in minutes. What is the y-intercept and what does it represent? Well, for the y-intercept, remember, just plug in 0 for x. So we are looking for f of 0. This polynomial is in standard form, which means all the terms with x's end up canceling out, and the y-intercept ends up just being that constant term. So the y-intercept is 65.8. So that's my y-intercept. To do the interpretation for this, just look at the units. Well, x is time in minutes, so we have an x value 0 for the y-intercepts. So after 0 minutes, of being left in the room, well, what does y represent? Y represents the temperature in degrees Fahrenheit. So the temperature of the cup is, well, the y value is 65.8, and the units were degrees Fahrenheit. So after 0 minutes of being left in the room, the temperature of the cup is 65.8 degrees Fahrenheit. And that's the representation of the y-intercept. When you're interpreting graphs or values from graphs, you just use both the x value and y value and their corresponding units in the description.